My name is Matt Dupree, and I'm going to be giving a talk on some lessons that we've learned from optimizing Citus queries at Heap. So quick disclaimer and a little bit about me. So I've been at Heap for a couple of years. I joined in March of 2020, and I've actually only been doing performance work for about a year. And when I first started doing performance work, it was actually a little bit intimidating. People were using terms like pushdowns and shard sampling, and I actually, it was a little scary, but yeah, here a year later, things are not so bad. And I actually have a screenshot or a selfie of me when I first started doing perf work that really kind of captures the angst that I was feeling. There it is. That's me. Just kidding. So yeah, I started working a year ago, and now I feel pretty comfortable, and I want to share some of the lessons that we learned from doing performance work. So here's kind of an outline of the talk. We're going to talk about the performance challenge at Heap, why it's kind of difficult to have fast queries at Heap, and then we're going to talk about 3 concrete performance lessons that we've learned this past year. So really quick kind of intro to Heap. Heap is a product analytics company. And typically the way that people do product analytics is they instrument their code with code that looks something like this. Let's say you have some sort of sign up button, and you want to track when people are clicking that button. Basically what you would wind up doing for a typical product analytics solution is you would add a track call, this track function call here, and that's how you would track whether somebody clicked a sign up button. Heap works differently. So instead of instrumenting your code, what Heap does is it actually captures all events that happen on a page automatically. And once all of those events are captured, then a product manager or a marketing professional can use a visual tool for selecting which events they're interested on the site. So what we're looking at here is somebody wants to track this Get Started button. And so they can kind of just do that visually. And so this approach, as you might imagine, means that we have quite a few events that we're processing. It's billions of events per day because we're capturing every event that happens on all of our customers' sites. So not only are we capturing billions of events a day, but we also want our customers to be able to query those events in real time. And when they construct a query where they can slice the data in pretty much any way, we need those queries to be the P90, the 90th percentile of the performance for those queries needs to be less than 10 seconds. And so we have a lot of data that we need to be able to query very quickly. So that's kind of the performance challenge at Heap. And now we can kind of get into the 3 performance lessons that we've learned this past year. So the first thing to note is if you've done kind of query performance optimization, the typical way of doing that with Citus or Postgres is to look at a query plan. And so you look at a query plan, and it kind of breaks down what the specific tasks that are happening under the hood to actually satisfy a query. And so this is usually enough for performance tweaking, but in our case, it wasn't enough. We would look at a query plan, we would try to optimize something, and it would look like it was faster, and we would say to ourselves, "Oh, we did it! Like it's fixed, it's faster." And we would say this because we looked at a query plan for a particular customer, and we saw, we made some tweaks, and we saw that the query went from running in 10 seconds to running in 6 seconds. But upon further investigation, we actually, when we're looking at different customers B and C, for example, we would see that there's actually no performance improvement in spite of the changes that we made. And so we would have to come back and say, actually, we didn't do it. And this wound up, making us look kind of clownish. And so we needed to find another way to kind of systematically evaluate whether we are making our queries faster with the changes that we made. And the reason that this was happening, there's a nice quote from this book on PostgreSQL query optimization that kind of explains why this happens. So I'm just going to quickly read this. It says, "There are no winners and losers among data access algorithms. The choice of an algorithm depends on the statistical properties of the data." And so what was basically happening is we were looking at a query plan, and we were seeing, particular nodes in the query plan, particular data access algorithms. And we're saying, oh, this isn't fast in this case. Let's try and get the planner to choose a different algorithm. the problem with that is that that algorithm may not be fast among other customers. And Heap has a lot of different customers, and those customers have the data of those customers have different statistical properties. And so the data access algorithms that are going to be appropriate for scanning through that data across the customers is actually going to be different. So there's actually kind of some noise when you're measuring performance for a particular customer or a set of customers, just related to the fact that the statistical properties of their data is different. There's also noise because when we actually perform our performance testing, it happens at a particular time of day, and there may be other load on this, contention on the system or load that the system's dealing with, which can affect our performance measurements. Or if the data is cached, that can kind of introduce some variability and noise into our performance measurements. And so in order to address this, we actually started constructing confidence intervals around our performance estimates. And so what we're looking at here is a visualization of the P90, P70, and P50 of the performance of the queries. And you can see that at the top, the middle, and the bottom of this visualization. And the dot it shows the actual performance estimate when we actually ran it across, let's say, a few hundred accounts. And then the bands, the interval here, it kind of looks like a TIE fighter. Those show the confidence interval, the 95% confidence interval. So on the left, that shows us, kind of optimistically how fast it may be in spite of the, the noise that we're seeing in the measurement. And on the right, it shows us the slowest that it may be in that 95% confidence interval. So that's something that we started doing kind of as a bare minimum. And the next step for this was to actually apply these confidence intervals to our performance experiments. So what we're looking at here is a similar visualization where we're showing the confidence intervals for the performance of a query, a control query, which you see on the red on the right here, and then an experimental query, which you see on the left in the green. And what we're seeing here is that there's a statistically significant difference between the performance characteristics of the experimental query versus the control query. And so now when we made our tweaks to the SQL or added an index or some sort of configuration change, we can be confident that this is a real statistically significant difference in performance. It's not, the result of some sort of noise of running it at a particular time of day or running it for a particular customer or running it when the cache is warm. And so this has been really helpful for us, and this was kind of a first step in optimizing our queries. So this is kind of the first lesson, is to perform proper performance experiments when you're optimizing queries that are kind of subject to the noise that's similar to what we see. So that's that lesson. Let's go and talk through a second lesson, which is how to get index-only scans on column expressions. Now, index-only scans are, we're going to talk a little bit about what they are in a second, but I just want to say at a high level, index-only scans are kind of our go-to way of making queries fast at Heap, because we've actually found that index-only scans have performance that is pretty similar to what you would get if you were working with a column-based data store. And so what's really nice about these index-only scans is that we can get performance that's similar to a column-based data store while remaining on Postgres, which is row-based. And so this is something that we've just found, that index-only scans are really important. Now, what are they? Let's quickly talk through what they are. So let's say that you have a table, an events table. And let's say that you have an index on that table that indexes on time and user ID. So if you have this table and this index, we can kind of represent this with a picture like this. And on the left, we can see the index, which has the time and the event ID. And on the right, we can see the table itself. Now, let's imagine that we wrote a query that looks something like this, where we're selecting just the user ID and we're filtering on time. So if you look at the columns that are actually referenced in this query, both of those columns are actually in the index. And so because both of those columns are in the index, we're actually able to get an index-only scan in that case. And what that means is that in order for Postgres or Citus to satisfy the query, to collect the data for the query, it doesn't actually need to visit the table itself on the right. It can just look at the data in the index. And this winds up being a lot faster, like I said at the outset. Now, let's let's kind of mix this up here. Let's say that we took this query and we added just another clause to the where statement. And so now we're not just filtering on time, we're also filtering on the type of the event in the events table. And so Heap captures lots of different types of events, clicks, field changes, touches on mobile devices. And let's say we just want to filter down to those 3 different types. Now, if we wrote a query like this, let's say that we also had an index like the one that you see here, where we have the type of the event, the time, and the user ID. You might expect that with an index like this and a query like this, you would actually get an index-only scan, because all of the columns that are referenced in the query are also present in the index, just as before. If you expected this, you actually would be mistaken. You won't get an index-only scan. And this surprised us, and this was similar to an issue that we ran into when we were optimizing a query for a feature. And the problem is actually is this data type column expression here. And the specific problem here is that the Postgres planner is not smart enough to realize that it does not also need data in the index. And so if you, the recommended kind of workaround is to actually add data into the index here. And you can see that at the top. I've bolded this data column that we're adding. This is kind of the only way that you can get the Postgres planner to realize that it can do an index-only scan. You need to add data type and the data blob itself. Now, the data column itself. Now, this was a problem for us because in our schema, there's a lot of data in that data column. And so this would result in kind of an unacceptably large index. Now, if this seems like kind of too silly to be true, or if the Postgres planner seems like almost really dumb in this case, the Postgres docs actually agree with you. Like, they just admit that the planner is not very smart about such cases. Fortunately, we were able to work around this, and we actually were exploited a way that the Postgres planner is actually kind of smart by restructuring the index. So we took this index, and instead of trying to put the data type column expression in the index, we actually turned it into a partial index where we're just indexing on time and user ID, and our where clause actually matches the where clause of the query. And we can see that here. So we bolded the where clause of the index declaration and the where clause of the query. Now, in this case, we actually do get an index-only scan. And this kind of makes sense if you think about it, because the user ID is in the index, the time is in the index. We can see that these things are bolded. And then the where clause of the query, this data type in click change touch, matches the where clause of the index declaration. And so Postgres actually does something kind of smart here. When it goes to look at the data to satisfy this query, it looks at the index. It notes that user ID is in the index, which you can see, and it notes that the time is in the index, which you can see on the far left. And then it notes that this index, this heap index here, only contains events where the type is click, change, and touch. So it knows that it doesn't need to visit the event table in order to check whether the event type satisfies the predicate here, because it knows that only events that satisfy that predicate are in the index. So in that case, we can actually get an index-only scan. And what we're looking at here is just a visualization that actually shows how much faster the queries were as a result of this when we did the performance experiment. We can see that it's about a 2x win at the 90th percentile, which was really great for us. So that's the second lesson, how to get index-only scans on column expressions. Let's talk about the third lesson, which is about audit tables and how they're underrated. So audit tables are great. I didn't know much about them before I started working on performance. And specifically, they actually saved us from breaking event ingestion at Heap. So let's quickly kind of talk about that. So in order to talk about how audit tables are really useful, we have to talk a little bit about how Heap Citus installation is set up. So here's a quick diagram that just shows kind of how Citus works at a high level. On the left, you can see that Citus kind of provides this nice abstraction where we can write SQL, kind of ordinary vanilla SQL, and without really having to worry about the fact that our data is distributed across a bunch of worker nodes on different machines, different data centers, doesn't matter. And what Citus does is it actually translates that vanilla SQL into SQL that will be executed on different nodes, different workers. And a key part of this diagram is this table metadata. This actually explains what data lives on what shard. And so our metadata looks something like this because we have two different distributed tables. We have a users table and an events table. And you can see that there's these user and events tables, they kind of come in pairs. They have matching node names with the same IP addresses. There needs to be both a user shard and an event shard on that same node. They need to kind of exist on that same node. And the reason for that is sometimes we want to execute queries that look like this, where we're basically joining across the events and the users table. And if the events and user shards don't exist on the same worker node, what Citus will have to do is actually shuffle data across the network, which will just kill the performance of the query. And so we have an invariant that's baked into our event ingestion code that checks to see if a given worker has matching event and user shards. And if it doesn't, it just doesn't ingest events anymore. And because it needs to make sure that our performance is going to be good after we ingest the data. So if that invariant's not satisfied, we don't ingest any events. If it is, then we'll go ahead and write the data to the worker. Now, let me go back a second. So that's an invariant that needs to be satisfied. And as a result of that, you can imagine that changing the metadata on the coordinator about where the shards live is actually a potentially dangerous operation. Unfortunately, it's not something that we can avoid at Heap. We need to be able to change that metadata sometimes. And one case where we needed to do this was we were actually considering a schema migration. So this is kind of what our schema looks like currently. We have time, user ID, and then a lot of data in a data blob, a data column, JSON B blob. And we were considering a new schema where we wanted to pull some of the properties of that data blob out into first-class columns in order to see if we could improve performance. And in order to do this, we actually needed to change the metadata. We couldn't just do something like an alter table statement, because while an alter table statement is being run, you can't insert anything into a table. And it would take a very long time to alter the table for the amount of data that we have. And so instead, we settled on an approach that looks something like this. So if you look at this diagram, this is similar to the kind of Citus high-level diagram that we looked at a few slides back. So we have the coordinator node on the left and the worker nodes on the right. And you can see that on the left, we have this mapping from shard 1, 2, 3 to worker 2. And then we can see on worker 2 on the right that there is shard 1, 2, 3. So the approach that we landed on was to basically first add a copy of shard 1, 2, 3 onto worker 2. Then we would update the coordinator metadata so that there's a mapping between shard 9, 1, 2, 3 and worker 2. Next, we would remove the mapping for shard 1, 2, 3 and worker 2 on the coordinator. And then finally, we would delete shard 1, 2, 3 from worker 2. And this would allow us to basically perform a distributed schema migration without halting event ingestion. So this was, at a high level, the approach that we settled on. Unfortunately, there was actually a bug in how we updated the metadata code, the metadata on the coordinator. And specifically, the bug was with how we computed the new shard ID. So the new shard ID that we kind of represented with these X's here was actually too large for the coordinator because of this bug, and it was rejected. And so we wound up in a state where the coordinator didn't have a mapping to worker 2 for the original shard 1, 2, 3 or the new shard ID. And so this violates the invariant that there must be an events and user shard matching on every worker. And so as a result of this, we had latency in our event ingestion, and this is what our Datadog dashboard looked like. And so this caused an incident, and we needed to address this. Now, because we had audit tables, we were actually able to do this with a really simple line of SQL. Here, we're selecting shard ID and node name from this audit table, and we're filtering down to actions that have occurred on that table that are delete actions that have occurred in the last minute. And now that we've grabbed those rows, we can go ahead and insert them back into the table, the coordinator table that has the metadata that maps between shards and workers. So the audit tables really saved us here, and I want to quickly go over how they work, just at a high level. So here's a trigger function that enables us to have this audit table. And we can see that it looks kind of like a UDF, but it returns a trigger. And we can also see that we can declare variables just like an ordinary trigger or an ordinary UDF, and there's a begin block. And if we look at this first part of the begin block, there's something interesting going on. There's a tgop variable that's present even though it wasn't declared in the declare block. And because this UDF returns a trigger, and it is a trigger, we actually have access to these special variables that make it really easy to actually create an audit table. So tgop, for example, stores a string that just represents what type of operation is happening on the target table. So in this case, it's an insert. tgrel_id is just the rel ID of the table that's being modified, and new is actually all of the it could be all of the columns for the new record that's being inserted. And so with these variables, it's easy to insert an entry into an audit table, and the rest of the function kind of works in a similar way. And so this trigger function is really the main piece of what you need to have a nice audit table. And then once you have it, you can simply wire it up with a SQL statement that looks like this. And so given how little effort it is and how useful these audit tables can be, especially if you're working with Citus and mucking with the metadata, I highly recommend creating these and executing these kind of few simple SQL statements. So those are the 3 lessons. So this is kind of quickly recapping what we covered. We kind of talked about the performance challenge at Heap, the fact that we're ingesting billions of events a day, and we need our customers to be able to query those events with a P90 of less than 10 seconds. We talked about 3 lessons, one of which was to perform proper performance experiments when trying to tweak SQL and make it faster. The second lesson was just a trick to get index-only scans on column expressions. And then the last lesson we just covered, just to use audit tables when you can. So those are the lessons that we wanted to cover. I just want to quickly note that we are actually hiring at Heap. If these problems sound interesting to you, go ahead and click the referral link here. Or if you want, you can reach out to me at Twitter. I'm at Philosophacker, and yeah, my name is Matt. So yeah, hope you enjoyed the talk.